This conference will now be recorded.
Hello everyone. Last day we have finished physical properties of alkanes and today we'll start chemical properties of alkanes. So alkanes, they are earlier called as paraffins. Now the meaning of paraffins in Latin is, this is the source word which means P-A-R-U-M, param, which means little, and affinis. This means affinity. That means the total term will be little affinity. So they have basically little affinity towards general reagents. General reagents means, you will see whenever we discuss chemical properties for any particular class of compounds, there are some common general reagents we always talk about. For example, how a substance, particular substance reacts with acid, how it reacts with base, or any other reagent such as any metallic catalyst, etc. Okay, so for general reagents with which most of the substances are react, okay, oxygen also you can consider a general reactant, fine, but they have little affinity, that is alkanes have little affinity towards all these general reagents under normal condition. Now if you apply some drastic conditions such as high temperature or high pressure, then the case is different. But whenever you consider normal condition, the general reagents that we generally consider, then there is very little affinity for alkanes. And this is expected also, because alkanes means what? Alkane means there will be CC bond and there will be CH bonds. Now both these bonds are very non-reactive in nature. Why? Because CC bond, it is the bond between two same elements. There is no such polarity, right? And also the electronegativity difference between carbon and hydrogen is very low. So the second bond also, that is to break this bond also, it is very difficult. So that is the reason, as in alkanes we have only these two type of bonds and both these bonds are very non-reactive. So to break these bonds it requires more energy, and that is the reason why they have little affinity towards general reagents. Okay, they are non-reactive because of this non-polar nature, and also another very important reason is there is no pi bonds. You have only sigma bonds, because compared to pi bond, if you consider sigma bond, that is if we simply compare pi bond and sigma bond, to break pi bond is basically easier process, because in sigma bond there is head-on overlap. It is a very strong interaction, but if you consider pi bond, which is sidewise overlap, the interaction is comparatively less stronger, right? So to break pi bond is very easy, but in alkane we do not have any pi bond. If you consider alkene where CC double bond is present, if you consider alkyne where triple bond is present, in both cases you have pi bonds, right? So compared to alkane, if you see in case of alkenes and alkynes, they are more reactive, but that reactivity you cannot expect in case of alkenes because of lack of pi bond and also the non-polar nature of CC bond and CH bond. They are least reactive of all the hydrocarbons. So this chapter is all about hydrocarbon, and there are what are the type of hydrocarbon. Remember the classification of hydrocarbon. There we have seen alkane, alkene, alkyne. Then there is aromatic compounds. But except alkane, in all other cases you will find some pi bond. Only in alkane there is no pi bond. So that is the reason they are least reactive compared to other hydrocarbons. They take part in reaction only under favorable conditions. So if you apply some special condition, that is drastic condition, then only reaction is possible. Fine. So the first reaction under chemical properties, it will be halogenation. Number one. So as the name suggests, halogenation. So obviously halogen will be the reagent. And in alkane, when you replace one hydrogen with some halogen atom by using any of the halogen in presence of heat or light, now instead of one RH bond, you are getting one RX bond. And the byproduct is this H is reacting with another X, and we are getting hydrogen halide as the byproduct. And these reactions you should notice very carefully, because if it is asking what is the mole ratio in the balanced equation, the mole ratio of alkane and halogen is 1:1, because the other atom in the X2 molecule, which is diatomic, it will take this H and it will produce HX as the byproduct. So this reaction we do when we are treating it with suitable halogen in presence of UV light or diffuse sunlight. So this is obviously drastic condition. It is not normal condition. Look at the temperature. It is very high temperature. Fine. Now, which halogen will react strongly? This is the order. F2 maximum strength with which it will react. Iodine is the minimum. Now, chlorination or bromination, these two are mostly used because fluorine is too strong. You cannot handle the reaction very easily. That is, experimental observations, everything will be difficult. There will be lots of byproducts. That is the problem. It's so reactive. Now, iodine, there is some other problems. We'll discuss it separately. But in between these two extremes, when you consider Cl2 and Br2, that is chlorination and bromination, these two are widely used. And most of the examples you will see or problems that you will get regarding halogenation, it will be mainly Cl2 and Br2. So fluorine is very quick because of its strong, that is, fluorine itself is very reactive, right? So that is why reaction with F2 will be very quick. And for iodination, that is the another extreme. Now the problem is it is too slow. So in between these two extremes, for chlorine and bromine, we discussed most of the examples. Okay. Now some important observations in the halogenation reaction of alkanes we have to know. During chlorination of methane, suppose you have taken methane as the hydrocarbon, you are replacing CH bond with CX bond. Chlorination, obviously it will be CCl bond. Now in this case, there is a chance of formation of mixture of products. Bromine reacts with alkanes in a similar manner, but the chance of getting mixture of products, it is not so high. Now look at these reactions. This is the first reaction. Up to this point, you can compare with the previous general equation where one RH bond, that is carbon hydrogen bond, is replaced by carbon halogen bond. But suppose if it is further reacting in other steps, second step, third step, then mixture of products possible. So first expected product is CH3Cl, which is chloromethane. But this chloromethane can be the starting material for another halogenation where the second hydrogen will also be replaced. And now you are getting dichloromethane. Now this can be again a starting material for the third reaction. Now you are getting trichloromethane. This can be again the starting material because still you have one hydrogen which you can replace. So ultimately all the hydrogens are replaced. You are getting tetrachloromethane. So this type of getting mixture of products, it is more in case of chlorination, but for bromine it is not so like that, because if you simply compare chlorine and bromine, which one is more reactive? Obviously chlorine is more reactive. So that is why this type of mixture formation, that is the probability, is comparatively high. Now the mechanism of chlorination we will study, and remember this is a radical mechanism. Okay. So here we will first step that we will take chlorine molecule. So chlorine is diatomic molecule. You can write it like this. But how many? That is that all the lone pairs if you place, there is actually total 3 lone pair per chlorine. Like this. And 2 electrons that are involved here. So per chlorine it is basically 7 electrons because that is the valence electron for halogen. Here, this bond, there will be homolysis. So, one electron will be with each chlorine atom. So, basically, you will get 2 Cl dot. For simplicity, you can also write it like this, simply ignoring the lone pairs. So, this step is called initiation step. Now, this is not just for chlorination. In any radical mechanism, the first step is always initiation step. Initiation in what sense? In the sense that when the first radical is formed, the step is initiation. Now, if the first radical is not formed, the further reactions are not possible. So we now have in our hand chlorine dot radical. Now the second step is propagation. But some other radicals also you will get, and one radical will react with another radical, or one radical will one radical not react with another radical. That is a termination step. In propagation step, mainly what happens, one radical react with a neutral molecule. So here the Cl dot that we have obtained in the first step, that will react with methane. This is basically methane. We have written it in this way so that you can understand how homolysis is occurring in the CH bond. So 1 electron for hydrogen, 1 electron for carbon. Now if this H is attached to Cl, you will get HCl as neutral molecule, and this will be your newly generated carbon radical, CH3 dot. Now this CH3 dot in the second step, it is reacting with a diatomic chlorine molecule which is neutral. So if there is homolysis occurring, one Cl dot will combine with CH3 dot and you will get your product, which is the actual halogenation product, right? And this Cl dot is still there, which can further react with another methane molecule, and in this way these steps will continue and continue. Okay. Termination step is the last step. Now termination step means in any radical mechanism, these three terms are very, it is common terms: initiation, propagation, termination. Termination means from the name itself you can understand. Now two radicals will combine together and you will get a neutral molecule. So ultimately there is no radicals left. So now the possibilities are so many. There is combination of 2 Cl dot possible, combination of 2 CH3 dot possible, or 1 CH3 dot 1 Cl dot. Because in the medium you have two types of radical. Cl dot you already have generated in the initiation step, and CH3 dot is also produced in the propagation step. So now you have two types of radical and all the possible combinations we can get here. So three types of molecule. This is our desired molecule, fine, but these two will also be produced as byproduct. This is not our desired product, but this can also be formed during termination. Actually, there is no such rules for termination. Any two radicals are very reactive, you know. So obviously, whenever a radical gets another radical, it is always jumping to it and it will form some neutral molecule. So we cannot give any guarantee that which molecule will be more formed better. But still, this will be our major product. Fine. Selectivity in halogenation. Now, selectivity means what? Selectivity means the previous example that you have seen, which is for methane. In that case, you have just one type of hydrogen. What I mean by one type of hydrogen? Methane means what? You have total 4 carbon hydrogen bond and all the carbon hydrogen bonds are equivalent. But suppose you have an alkane where you have different types of hydrogen. Now, if you are thinking that is it methane? Is it ethane? Now in ethane also, if you see, all the carbon hydrogens are basically equivalent. But if you consider propane, now all the hydrogens are not equivalent. There is two types of hydrogen, right? So for the two terminal carbon, these three hydrogens are attached to the carbon, and this middle carbon, these two hydrogens, if you consider, this carbon is attached to two carbons. So these two hydrogens are 2 degree. This carbon is 2 degree because it is attached to 2 carbon. And the hydrogens that is attached to 2 carbon, 2 degree carbon, that is also 2 degree. So the rate of replacement of hydrogen of alkane, when the question arises, it is not applicable for this or this because all the hydrogens are equivalent. But when you take propane, now these three hydrogen, these three, total 6 types of hydrogen, 3 and 3. But for these two, it is different. So we have 2 hydrogen, which is 2 degree, and we have total 6 hydrogen that are 1 degree, right? Now the rate of replacement 3 degree, 2 degree, 1 degree. So in this case, you do not have 3 degree, but you have 2 degree. So the chance that these 2 hydrogens will be replaced by halogen, that probability is higher compared to the other 6 hydrogen. What is the reason behind it? The reason is it is a radical mechanism, and when you have 2 degree radical, that is more stable. And details of radical, why it is more stable, everything we have discussed in the previous unit, which is basics of organic chemistry. There we have already seen that. So as 3 degrees radical more stable than 2 degree, because when you break this CH bond, the dot over carbon, that carbon is more stable. So because of this stability, we get this type of order. The rate of replacement of hydrogen of alkane is like this. Now this selectivity, it is seen that is experimental observation is saying when you compare selectivity in case of chlorination and bromination, it is observed that selectivity in bromination is considerably greater than the chlorination. Okay. So what it means, with example you will be able to understand. Here we have taken propane and we are treating with propane chlorine, and also the second reaction again we have taken propane, but now instead of chlorine we have taken bromine. Now see, this is the first product where 2 degree hydrogen is replaced, and this is the product where 1 degree hydrogen is replaced by the halogen. And look at the ratio. Obviously the 2 degree hydrogen replacement rate is high, it is 55, this is 45. But still these two values are very close to each other. But when you consider bromination, the rate at which this H is replaced by Br and the rate by which the terminal hydrogens are replaced by Br, look at this value 97.3. So in both cases it is selective, that is fine. This is measured, this is measured. But from the percentage you can understand that selectivity is obviously high in case of bromination. Now we will take this part, and now if you are still curious to know what is the reason behind it, that actually requires details of the mechanism, details of the energy profile diagram. Obviously we will not go into that. That is not required for our purpose. So just remember this, that selectivity is more in case of bromination. Here we have taken one more example, and you can see different types of hydrogens are there. Now this is symmetrical, that is fine. Now these two hydrogens, they are basically 2 degree. This is also 2 degree. But here these three, this is a methyl, this is a methyl, this is a methyl. So 3 hydrogen, here also 3 hydrogen, here also 3 hydrogen. These hydrogens are 1 degree, right? And there is 3 degree hydrogen also, which is this one. So total 3 types of hydrogen you already have. Now the chance that you will get how many types of mono bromination is possible. Obviously we are talking about monohalogenation, because when we are talking about selectivity, at least one thing you have to fix. If you consider that is not just monohalogenation, if you consider dihalogenation, it will be very complex. So just focus on monohalogenation and try to understand selectivity. Here we have total 3 hydrogen, this is 1 degree, 3 hydrogen, this is 1 degree, this is also 1. Then 2 degree, and we also have 3 degree. So total, what are the possibilities we will get product? First of all, how many different types of hydrogens are there? That is the question. Now, different types of hydrogens are there. It is basically, I'm numbering it. Suppose these are the A hydrogen. This is also A hydrogen. This is B hydrogen. And this position is C hydrogen, where 2 degree is present. And this position is D. So these are the different positions. So total 4 types of product you can get. Now, among these 4 types of product, the product that you will get from the replacement of D hydrogen, that will be basically going through 3 degree radical. And from the C, that will be going through 2 degree radical. And from A and B, that will be going through 1 degree radical. So these are the possible products. So the first product you are getting when A type of hydrogen is replaced. The last product when B type of hydrogen replaced. This product is when C type of hydrogen replaced, and this one is when D type of hydrogen is replaced, right? Now, which one will give you the major product? Obviously, this will be the major product because this is 3 degree, right? And in case of this one, that is C, which is 2 degree, this will be minor. And what about the last two? This will be compared to minor, you can say it will be very minor. That is, percentage will be very low. So in this way, you can understand the selectivity. Now, another important point is also there, which is known as statistical. Now, what I mean by statistical, here simply consider propane. Here you have 2 degree hydrogen, total number is 2. If you consider 3 degree hydrogen, total number is 6. Though we know that 2 degree is more stable, 3 degree, sorry, not 3 degree, 1 degree. 2 degree is more stable than 1 degree, that is fine. But number, if you compare, it is still 1/3 of the 1 degree hydrogen. So from statistical point of view, the chance of getting the replacement of terminal hydrogen, that is also very high if you simply omit the fact of stability. So that is also very becomes very important in case of chlorination. So that is why, though this product is this radical is through which this is formed, it is more stable, but from statistical reason also this percentage increased. But in bromination, the selectivity is so high that even if the terminal hydrogens, they are higher in number, but still the product is very less. That means here selectivity is really very high. Okay. Now we'll talk about something about iodination. We know that this is slow than the other three. So the reaction of iodine with alkane, it is basically reversible in nature. So the chance that you will get product, but again you can get back the original starting material. The reason is the HI which is formed as the byproduct. We know in halogenation, when you replace RH bond with remember the general equation that we have already seen. You are reacting it, then from RH you will get X and there will be formation of HX. Now in iodination, this HX is HI, right? Now this HI, it is a moderate reducing agent. So what it can do, it can reduce this iodoalkane, and the Ci bond again can be converted to CH bond. So this is the problem we face in iodination. But there is a solution for it. If somehow you can remove this HI, then the equilibrium will be shifted towards right hand side according to Lee-Chatelier principle, right? So iodination can be carried out in presence of some oxidizing agent such as HiO3 or HNO3, which can oxidize iodine HI to iodine. And this is a reaction. HiO3 reacts with 5HI, converting it to 3 iodine and 3 water. Similarly, HNO3 can react with HI, and the products we get, iodine obviously will be there, and these are the byproducts. So in this way, by using some strong oxidizing agent, we can remove the side product HI so that it cannot reduce our desired product CH3I back to starting material. Okay. Now we will solve this question. It is asking that maximum number of isomeric monochloro derivatives which can be obtained from 2255 tetramethylhexane by chlorination. So monochlorination you have to consider. But here name is given. So the first thing is you have to draw the molecule. These are the substituents. Total 4 methyls are there, but basic chain is hexane. Fine. Now at 2 position there is 2 methyl groups. At 5 position there is 2 methyl groups. So the groups I am just circling so that you can see them differently. In this molecule, you have to understand how many different types of hydrogens are there. Just we have already done. Remember, in case of propane, we have seen there is 2 different types of hydrogen. Similarly, you just have to understand how many different types of hydrogens are there. Now look at this molecule as a whole. Forget about the number. These 3 methyl groups, each having 3 hydrogen. These 3 methyl groups, each having 3 hydrogens. Total 9 hydrogens, all are 1 degree, and they are equivalent. So any of these CH bond you break, basically it means same thing. So these are type A. I'm just numbering it as type A. Now come to these 2 hydrogens, and these 2 hydrogens, they are 2 degree. So these hydrogens, suppose I am numbering them, calling them as B. So you have A type of hydrogen, 9 hydrogen, 9 hydrogen. Number is not important, I'm just saying. And you have B type of hydrogen, total 4. Now maximum number of isomeric monochloro derivative. So as 2 types of hydrogens are there. So obviously we'll get 2 types of isomers. When any of these A hydrogens you are replacing with halogen, then you will get 1 type of product. And when B type of hydrogens you are replacing with halogen, you will get another type of product. Okay. But is it the answer? you also have to check when you are replacing this hydrogen with halogen, is there a chance that it is optically active? Because if it is optically active, then you also have to consider its enantiomer, because it is asking isomeric monochloro derivative. So all the isomers we have to consider. So this is the molecule, same molecule. See, this B hydrogen, B hydrogen, A hydrogen, A hydrogen. Now when we are replacing A hydrogen, we will get product number 1. Now this molecule is optically inactive. There is no chiral center. But in the second one, when you are replacing B type of hydrogen, this carbon is basically chiral, because with this carbon you have 4 different groups. One is H, another one is Cl. This is one large group, tertiary butyl group. Then we also have this group. So all the 4 groups are different. So this is a chiral center, plus minus 2 enantiomers possible. So here we are getting total 2. This is 1. So 2 plus 1, the answer should be 3. Okay. Number of bromo derivatives obtained on heating ethane with excess of bromine in diffuse sunlight. Now the question, if you read carefully, it is not talking about any monobromination. It is simply saying that ethane is in presence of excess of bromine, diffuse sunlight. That means there is a chance of more than one time further bromination is also possible. So you should not consider only monobromination. You also have to consider all the possible bromination. So that is why it is asking. It is an integer type of question. What is the total number of bromo derivatives you will get? Whether it is mono bromination, dibromination, tribromination, whatever. So the molecule given is ethane, CH3CH2. Now the first possibility is obviously monobromination. Now when it is monobromination, how many different types of products possible? So here all the hydrogens are equivalent. So monobromination, you will get only one type, only one. Now when it is dibromination, it may possible that from same carbon 2 hydrogens are replaced. This is CH3. In that case, you will get this molecule. But if one hydrogen from carbon number 1, suppose this is carbon 1, this is carbon 2. One bromine from carbon 2 we are getting. Then 2 different types of possibilities are there when it is dibromo substitution. So here we have 1, here we have total 2. Now when it is tribromo derivative, now it can be that 2 bromine atoms are attached to same carbon and 1 bromine at the other carbon, or it may be all the 3 bromine in the same carbon. So the possibilities are, again you are getting 2 types. But first possibility is bromine from C1 and 2 bromine atom in C2 attached. And in the second case, all the bromine in the same carbon. So total possibilities again 2. Now the next is 4 times bromine. 4 times carbon hydrogen bond will be replaced by bromine. Now when it is 4 times, it may be that 2 bromine, that is 3 from here and 1 from the other carbon, or it may be 2 from one carbon, 2 from one carbon. So again 2 possibilities. Number 1 carbon, number 2 carbon. Okay, you cannot get any more possibilities than this. And then we have 5 substitution. Now when it is 5 times substitution, obviously only one possibility is there, and when it is 6, it goes without saying there is only one possibility. So total how many we are getting? 3 times 1 and 3 times 2. So 3 into 2, 6, and then 3 more. So it will be total 9. Okay. The next reaction after halogenation is nitration. As the name suggests, it is replacement of carbon-hydrogen bond with a nitro group. Now the source of nitro group is, it may be either HNO3, most of the times you will get HNO3, or it may be N2O4 also, nitrogen tetroxide. So these will be your nitrating agent. And the temperature is around 400 degrees centigrade. Sometimes higher temperature may also be required depending on whether the alkane is reactive enough or not. Because if the alkane is linear, simply linear chain, then it will not be very reactive. But suppose if there is a branching, more is the branching, more will be the chance that it will be reactive. And the reason is, this is also radical mechanism. So when there is more branching, the carbon radicals that are generated, the chance is high that they will be 3 degree or 2 degree. So this is the reason from linear chain you cannot expect reactivity that you can expect from branched alkane. So this is the reaction, the general equation you're seeing here. Now during nitration, sometimes CC bonds of alkanes can also be decomposed because we are using some strong oxidizing nature and the temperature is also very high. So there is a probability that you can get to produce all possible nitroalkanes. So very good example for this, you can consider the nitration of propane molecule around 400 degrees centigrade, in Kelvin it is mentioned. Now this is the normal product you are expecting, but this is only 25% where this terminal hydrogen is replaced. Now when this middle hydrogen is replaced, you are getting 2 nitropropane, this is 40%. So this is basically measured and that is expected because it is radical mechanism. So the radical that will be generated in the middle carbon, it will be obviously more stable than the radical that will be generated at the terminal carbon. So this is fine. This is major, this is minor. So these two we can expect. But now look at the next two products. These we at a first glance we do not expect because in this case one carbon is less. It is nitroethane 10%. Even 2 carbons can be removed. You are getting nitromethane which is 25%. And also there are some other mixture of oxidation products. So because of these possibilities of cleavage of carbon-carbon bond, though major product is our desired product, but still there is chance of getting so many other types of products because of the cleavage of CC bonds. The products from the mixture we can separate by fractional distillation that you have already we learned it in the previous unit. That is what is fractional distillation, when you have mixture of so many liquids that are having boiling point very close to each other, then fractional distillation is better method. All available evidence points to radical mechanism, but still there are many aspects of the reaction that are not fully understood. Because if you want to study a particular reaction, the reaction should be clean enough. But here the reaction is not very clean. What I mean by clean is that you are getting some product, but still there are so many other products. So that is, it is not very clean reaction. And when a reaction is not very clean, its study of the reaction, it becomes very difficult. So that is why many aspects of the reaction are not fully understood. Next reaction will go for alkanes. Number 3 is sulfonation. Sulfonation is replacement of hydrogen of alkane, that is carbon hydrogen bond. Now it is replaced with carbon SO3H bond. So that is why it is known as sulfonation. How we do it? We do it with fuming sulfuric acid, which is also known as oleum. Now fuming sulfuric acid is mixture of H2SO4 plus SO3 sulfur trioxide. You can also, sometimes it is written as H2S2O7, oleum, fuming sulfuric acid, very strong. Here we have some examples. First we have taken propane and it is mentioned here in presence of H2S2O7 that there is no reaction. But why it is so? We will come to that point. Then we have taken butane and it is linear chain. It is N-butane, right? No reaction. Unbranched alkane. Again we have taken 4 carbon, but now it is isobutane and there is a branching and we are getting product. So as I have said, more is the branching, more is the stability of radical, and the chance of getting product is high. So the reason you are not getting product in this molecule, though it is also containing total 4 carbon, just like the third reaction, the reason is here radicals are comparatively less stable. So when this H is replaced by SO3, the radical at first is generally generated at this carbon, which is 3 degree, and it is very stable. But that is not possible in case of second reagent, second substrate. So that is the reason no reaction is mentioned here. Then we have taken another branching compound. Here also we are getting product. Fine. So branch chain and higher normal alkanes. Branch, if it is very small carbon, that is total number of carbons are very small, suppose 4 or 5, then it has to be branched. But if you move to higher carbon number alkane, then you can take normal. Normal means linear chain, because now that factor will be overcome because of its higher normal alkanes. So that is why they can now undergo this reaction to give an alkane sulfonic acid. So these molecules are basically alkane sulfonic acid. So for lower carbon number, there must be some branching. So here we have a note that we have to understand that lower alkanes do not undergo nitration and sulfonation reaction under normal condition. By lower alkane, you can take these examples, that is ethane or methane or propane. That is lower alkanes, that is the first 3 members you can consider. You cannot expect any, and here branching is also not possible. So under normal condition, reaction will not be there. And not just sulfonation, it is also true for nitration. Mechanism of these two reactions we have already seen. It is radical mechanism, and that is the reason that tertiary or branched alkyl radicals are more stable. But branched alkyl radicals, tertiary alkyl radicals, you cannot get in case of lower alkanes. So that is the reason here we will have no reaction. Fine. Now the number 4 reaction is combustion reaction. So combustion reaction is reaction with oxygen. On heating, that is alkane, when you are heating in air or oxygen, there is formation of CO2 and H2. And remember, this heating in presence of air and oxygen, there should be full presence of oxygen. There should not be any controlled presence of oxygen. Because if that is the case, then instead of CO2, you will get another oxide, which is carbon monoxide. But that is not the case here, because when we talk about combustion, it is basically in presence of huge amount of oxygen. And remember, in combustion reaction, it is always exothermic. There is always evolution of heat. Heat is released, light is released, usually in the form of flame. So here we have taken the example of ethane. We are treating it with oxygen, and the product is CO2 and H2. Remember, the products of combustion, it is always carbon dioxide and water. And how to balance this type of reactions? It is very easy to do. Suppose just take this reaction. First, what you will do, you will write the hydrocarbon, and then in the right hand side you will write the products. So this will always be your products. There is no doubt about it. Now look at your hydrocarbon which you have written. Just write 1 mole of it first. In this hydrocarbon you have total 2 carbon. So from when there is 2 carbon, obviously CO2, it must be 2 CO2. It has to be. Look at the number of hydrogen in the hydrocarbon. It is 6. And the fate of hydrogen in the right hand side, it is water. So it has to be 3. Now count the total oxygen. Here you have total oxygen atoms 4. Here you have total oxygen atoms 3. 3 plus 4, 7 oxygen atoms, right? So it should be 7 by 2 oxygen. But if you do not like this reaction like this in this form, simply you have to multiply with 2. Then these 2 will be cancelled, and these 2 will be 4. These 3 will be 6. So that is why it is written in this way. So in this way, just following this rule, you can do this for any hydrocarbon. So just do it for C4H10, which is the next one. First, I will not write the oxygen. I am writing simply CO2 and water. Now total 4 carbon, that means it has to be 2, right? Sorry, it has to be 4. Total 10 hydrogen, so it has to be 5. Now total oxygen here is 8, 4 into 2, total oxygen here is 5. So 8 plus 5 is 13. So oxygen should be 13 by 2 O2. But if you want to multiply with 2, you can do so. So in this way, balancing combustion reaction is very easy. Since the process of combustion is accompanied by a liberation of huge amount of heat, so this we can apply for those cases where we need a huge amount of energy. So alkanes, which are the constituents of LPG, liquid petroleum gas, then gasoline, kerosene oil, diesel, they are used as fuels. So these names that you are saying, everything, there is a mixture of so many different types of alkanes. So when they burn in air or oxygen, there is formation of huge amount of energy, and that is why they can be used as fuel. If the combustion of alkanes is carried out in limited supply of air or oxygen, which I was just saying in the first point, that instead of excess CO2 or full presence, excess O2 or full presence of O2, if you have limited supply of oxygen, then instead of CO2, you get CO. But that is not combustion product. Combustion means it is always CO2 and H2. Along with carbon in the form of carbon black or soot. Remember, there are different forms of carbon possible, allotropes. So this is the reaction when you have limited supply. So this 2CH4. Now normally if you consider CH4, that is a full combustion, normal combustion reaction, it should be CO2 and 2H2. And total oxygen, as you can see, in CO2 2 oxygen atom, in 2H2 2 oxygen atom. So it should be 2O2. But instead of 2O2, that is for 1 methane, the requirement is 2 oxygen. It is 1:2, right? But in this case, see, it is 2:3. That means if you make it 1, it will be 3/2. So now it is basically 1:3/2, which is nothing but 1.5. So when you do not have this type of mole ratio between CH4 and O2, but you have lesser than this, we get CO and water as it is. Then if the presence is even less, now it is not 1:2, 1.5. Now it is 1:1. You are getting another different product. Okay. Minimum number of moles of O2 required for complete combustion of 1 mole of propane, 2 moles of butane. Okay. So propane and butane we have already moles O2 for completion, 1 mole of propane, 2 moles of butane. So 1 mole, okay, propane we have not done, 2 moles of butane. So for 1 mole of butane, this is the requirement, 13/2, right? So when there will be 2 moles of butane, it should be 13. So 2 moles of butane, the number of moles of O2, not monoatomic, O2. So it should be 13 moles. But for propane, we will write the equation C3H8. And this side there should be 3 CO2 and 4 H2O, just based on the number of carbon and hydrogen. Total oxygen here is 6 atoms, total here is 5, that means 6 plus 4, 10. So it should be 5 O2. So for 1 mole, the requirement is 5. So this is 5, this is 13. Now just add these two value, you will get total number, which should be 80. Fine. Next reaction here we have controlled oxidation. Now the previous reaction you can think that it is also oxidation, but when we are talking about controlled oxidation, it is not like combustion. Combustion is full oxidation, right? But here it is controlled oxidation and also in presence of some catalyst. And depending on what type of catalyst you have taken, what type of reaction conditions you are using, same starting material can give you different types of product. So in this controlled oxidation, in presence of different types of catalysts, mostly metal catalyst or metal related catalyst, there may be formation of alcohols, aldehydes, carboxylic acids when alkanes are exposed to oxygen. But obviously it is regulated supply, because if there is full supply, instead of these products you will end up with CO2. That is different reaction at high temperature and pressure in presence of different types of catalyst. So one by one we will see. Suppose you have taken methane and in presence of oxygen, look at the pressure, it is very high. So as I have said, depending upon what type of catalyst you have taken, what reaction condition you are using, product will be different. So alcohol we will get at this reaction condition when the catalyst is copper tube. You are passing this gas through copper tube, 573 Kelvin, you are getting alcohol. Again you have taken an alkane, this time you have taken ethane. Under pressure is passed over heated molybdenum oxide. This is also metal oxide, metal related catalyst. In this case we are getting the oxidation product which is CH3CHO. If it is methanol, if it is methane, it will be formaldehyde, HCHO. Alkanes on oxidation in presence of manganese acetate. Suppose you have taken this catalyst, you can also write it like this, MnOAc, OAc means CH3CO group. So this will give you fatty acid if it is this type of longest chain, where N value is very high. These are very higher alkane. But you can also do it for lower alkane. In that case, it will not be fatty acid. Then it will be like formic acid or acetic acid, ACOH or CH3COH like this. Okay. There is one more information important is, now this time the catalyst, it is not any KMnO4 salt. Normally oxidizing agent, we know this is a very good oxidizing agent. KMnO4, whenever we, suppose someone is asking you, tell me some good oxidizing reagents name. So this is the inorganic reagent that comes first in your mind. So KMnO4, it can oxidize so many things. Another oxidizing agent you can say K2CO2. But these KMnO4, they have no effect on alkane. But if you take some special type of alkane, which special? Suppose you have taken alkane containing tertiary hydrogen atom, such as Me3CH. So this H is tertiary, because this carbon is tertiary. Now in presence of KMnO4, this will have some effect. It can be oxidized to the corresponding alcohol. So in place of H atom, now you will get the group OH. So this is specially for tertiary hydrogen atom, not just for any alkane. Okay, there must be tertiary hydrogen atom present. So total 4 different conditions we have seen: copper tube, alcohol, molybdenum oxide, aldehyde, manganese acetate, acid we are getting as product. If it is higher alkane, it will be fatty acid. And when it is KMnO4 and only alkane containing tertiary H, then only you are getting corresponding alcohol, which is again alcohol, but not just any alcohol. It is only from Me3CH or any alkane containing tertiary hydrogen. Next reaction is number 6, isomerization. So one alkane will be converted to its isomer. Isomerization of alkanes involve conversion of straight chain alkanes into isomeric branch chain alkanes. Right? So here we will take example of N-butane. If you are heating it with aluminium chloride, this is the catalyst. In presence of dry HCl gas, temperature, this amount of pressure, you will get 2-methyl propane. So total number of carbon is still 4. Now we have one substituent, but it is 4 carbon. This is also 4 carbon. This is isomerization. So obviously the number of carbon will be same. Here is our 1-butane and this is 2-methyl. Propane. Similarly, if we take N-hexane, we can get two different types of product, 2-methylpentane or 3-methylpentane. So here we have taken N-hexane. 1, 2, 3, 4, 5. So it is 2-methylpentane. So this is having some importance from industrial point of view, because the quality of gasoline, which is basically mixture of different types of alkanes, you can improve it by isomerization reaction. So as I have said, it is a mixture of different types of alkanes. So if you want to increase the number of branch chain alkanes than the linear chain alkanes, you can use this isomerization reaction. In this way, what will happen? The amount of branch chain will increase and the quality of gasoline, that will also improve. Okay. Number 7 reaction is aromatization, which is also known as reforming reaction. It is, as the name suggests, starting from aliphatic compound, you will end up with aromatic compound. Now, as we are discussing chemical properties of alkanes, this aliphatic compound is obviously some alkane. So alkanes, when we have alkanes containing, look at the value, here it is mentioned as 6 to 10 carbon. So when we have this range of carbon atoms, we are heating it to 773, the temperature is high, 10 to 20 atmosphere, in presence of some catalyst consisting of, now the catalyst may vary, and the catalysts are related to this type of metals, chromium, vanadium, molybdenum, supported over alumina. They get converted into aromatic hydrocarbon. So look at this condition, 773 Kelvin, 6 to 10 carbon atoms. 6 carbon atoms must be there, because the simplest aromatic compound you can have is benzene, but 6 carbons you must start with. And catalysts are related to chromium, vanadium, molybdenum, which is supported over alumina surface. Here we have taken N-hexane, and N-hexane normally we draw it like this, but this time we have drawn it in a different way so that you can understand how the cyclization is occurring. The first step is cyclization, where one hydrogen from this carbon side, another hydrogen from this side, if it is removed, you are getting a CC bond. Okay, and here we have taken Cr2O3 on the surface of Al2O3, chromium oxide. Then in the second step, 3 more hydrogen diatomic molecule is removed, and that means HH, this has to be removed. Then HH has to be removed, so that you can get double bonds in these positions. So finally you are getting benzene. Now instead of taking hexane, if you take 1 carbon extra, then what will happen? So 2 steps are there, cyclization followed by dehydrogenation. First one is also dehydrogenation, but better you call it as cyclization, because we are getting from open chain, we are getting some ring compounds, so it is cyclization. And the second step, where hydrogen atoms are removed in the form of H2 molecules, so that is why we are calling it dehydrogenation. Now if you start with N-heptane, again we have drawn this molecule in this way, it will help you to understand the product. Same condition. Now these two positions are connected, you are getting methyl substituted cyclohexane, and after removal of 3 more hydrogen from these positions, now we will get toluene, methyl substituted benzene. This is also known as reforming. Number 8 reaction is reaction with steam. Methane reacts with steam 1273 Kelvin in the presence of nickel catalyst, and we get carbon monoxide and hydrogen. Now this type of production of H2 hydrogen gas starting from methane, it is known as steam reforming process, and it is a well-established industrial process for the formation of hydrogen gas from hydrocarbons. So it has from industrial point of view, it has some significance. CH4 with steam, which is basically water, it is written in this way. In the equation, we are getting CO plus hydrogen gas. Number 9 reaction is pyrolysis or cracking. Now pyrolysis, the term basically means, the word pyro means fire. And if you consider lysis, it means disintegration. So using very high temperature, when you are disintegrating something, it is called pyrolysis. This term you can also find in some other cases, not just for alkanes. So whenever you are getting the term pyrolysis in chemistry, it is basically, it means very high temperature, very drastic condition. There is some cleavage occurring. Okay. So pyrolysis is a process by which a solid or a liquid undergoes thermal degradation. So it's all about in the reaction condition, it is all about the temperature, which is very high. So that is why the name is like this, into smaller volatile molecule, and often it is done in inert atmosphere. Now in case of alkane, in absence of air, when alkane vapors, obviously the temperature is very high, so alkane will be in the form of vapors. Now you are passing it through some red hot metal, temperature 6 to 7 atmosphere, in presence or absence of catalyst, and that depends on the which alkane we have taken. But important point is it will be breaking down to some simpler hydrocarbon, because this is fire, that is pyro, fire, lysis means disintegration. Pyrolysis of alkanes involve not just CH bond breaking but also CC, because we are getting smaller units, simpler hydrocarbons, and that is only possible if it breaks CC bonds also. And the mechanism is free radical mechanism. Okay. Some more information related to pyrolysis, but we will not be able to finish it. So rest of the part of pyrolysis will finish in the next class. We are ending the session here. Thank you for listening.